All right, guys, good afternoon or good morning, depending when you're watching this video. This is going to be a tutorial for electric energy and capacitance, chapter 16 in the textbook. You have several videos where I go over examples and problems, and of course, you know what some of these concepts are about. They are a follow-up of Coulomb's law, electric forces, and electric fields. So showing you there kind of like a tutorial for the questions in WebAssign. Let's just go over, for example, question 1, where they give you a uniform electric field of, you have different numbers, but here I have 436 newtons per coulomb pointing on the x direction, in the positive x direction, acting on an electron at rest and makes the electron move certain distance. So if you want to find the work, done by the electron and the change in potential energy. All right. So if it was a proton, it will be probably a bit more straightforward because you don't have to worry about a sign. Basically, and that's EQ, right? The electric of the electron. If the force left, that will give you a negative work, if you think about it. Because then the change in potential energy, right? Now compute let's some reason my internet is well, I remember the electric field was 436. The charge of the electron 60 times and the electric newtons per coulomb. So later here, and this is still right now. So electric field is on the let's see before. So then the electric force will report force so we'll need this. So times 2.7. So times 10 divided by 10, 1.88. So that's the work. Potential energy. Meaning of a negative change. So that means that the force acting on the electron is to the right. But the electric field is going from right to left. The force is going from left to right. The work is positive. The change in potential energy is negative because you're going from a higher potential to a lower potential. Okay, so you are reducing your potential energy because the electric field normally goes from positive to negative, if you think about it, right? The electric field is pointing toward the left because you have positive charge here, negative charge on the left. That's why you're going from positive to negative, the electron. So the electron has a negative change on potential energy. Now we can find the speed of the velocity, of the speed of the electron due to that change. All right. Basically, we can just use the work and make it equals to the kinetic energy, right? Just like mechanics, right? The work done by the force is equal to the change on mechanical energy. There is no gravity here. Is just the kinetic energy, right? So the potential energy is equal to the kinetic energy. So this or this, we make it equal to the change of kinetic energy. Now, in the problem, they tell you that the electron is at rest. So if the electron is at the beginning at rest, that means that the initial velocity is 0. So the initial kinetic energy is 0. So then we can make 1.88 times 10 to the negative 18 equals to 1/2 mass of the electron times the velocity final square. Conservation of energy. So what's the mass of the electron? 9.11 times 10 to the negative 31 kilograms. So the final velocity is 2 times 1.88 times 10 to the negative 18 divided by the mass of the electron, square root of that. Let's see what we get in the square root. So 2 times 1.88 divided by 9.11. That's, and then the 13 there. So I get times 10 divided by 10. So 4.12 times 10 to the 12. If I take the square root of that, 2.03 times 10 to the 6 meters per second. So there you are. What you would expect for an electron like this. And in what direction? On the negative direction, because the electron is going towards the left. All right? That's pretty much how you do problems like this. Energy and a bit of forces. Problem 2 is similar. Let's do problem 3. What's problem 3? Let's show you. That's problem 3. You have a rectangle with three charges, 3-point charges, and you want to find the electric potential energy. Oh, the electric potential, sorry, at the upper right corner. So you have 2, 4, and 8. 2 microcolumns, 4 microcolumns, 8 microcolumns. Find the electric potential on the upper right corner. You want to find the electric potential here. Taking the potential at infinity equals to 0. That means that V at a very large distance equals to 0 volts. That's fine. Oh, what are the dimensions? 5.9. Let's make it 6 and 3. Make it easier. So let's make this 6. And let's make this 3. If that's 3, that's 3. If that's 6, that's 6. And you want that, right? So right triangle here. So the thing about electric potential, let's call it this point P, is that you can do an algebraic sum. It's just a sum. K, let's start with this, 4 microcolumns divided by 3 centimeters, 0.03, plus K, column constant, 8 microcolumns divided by 6 centimeters. And then I have this charge. Now that's 2. But what's the distance? I need the hypotenuse. 6 squared, 36. 3 squared is 9. A square root of 45. It's approximated. Should be around 7 point something. Oh, sorry, 6.7. So 6.7. So this will be 0.067. K is a common variable and 10 to the negative 6. So why do I write it like that? Because I can pull K out, which is 9 times 10 to the 9. That's K. And 10 to the negative 6. And then look, 4 over 0.03 plus 8 over 0.06 plus 2 over 0.067. 9 times 10 to the 9, 10 to the negative 6. That's 9,000. And then let's calculate what's on the parentheses. Right? Yeah, perfect. You can see everything there. So 4 divided by, that's 133. So let's do it here. 9,000. I get 133.3 plus, that would be 8 over 0.06. 133.3 plus 29.9. So I'm going to get a large number. That's fine. So I get 2,668,000 500 volts. Yeah, you want to leave it like that. Trying to keep the most amount of figures there. Okay. In part B, they ask you to change the positive 2 to negative 2. This is part A. In part B, basically, instead of 2, that's negative 2. So that will be negative, negative, right? So for part B, you will just change this. Negative, negative, and then here negative. So this is for part A. For part B, I'll get the same values, but now it's negative there. So caramba. Again, 2,130,000. So it's 2 million now, 130,300 volts. That's fine. All right. Same idea. Okay. Let's do question 4. Or let me see actually. Question 4, question. Let's do question 5 and 6 first. Capacitance. So let's do capacitance problems as well. Again, there's a video already with capacitance examples in there and circuits. But this is from Cengage, so it's going to help you with the problems on the assignment. When a 4.50 volts battery is connected to a parallel plate capacitor, the charge is 17 microcoulombs. What's the value of the capacitance? Okay. So capacitance is equal to charge over potential difference, over voltage. So if the voltage is 4.50 volts and the charge, or sorry, the capacitance, right? And the capacitance, or the charge is 17 microcoulombs, what's the value of C? C equals to 17 microcoulombs. Don't forget 10 to the negative 6 divided by 4.50. That's 3.78 times 10 to the negative 6 farads, which is 3.78 microfarads. Easy. That's an easy problem. Let's do number 6. They give you an air-filled parallel plate capacitor with a given area, with a distance between the plates, and the voltage of the battery. So they ask you a few things in there. So if they give you a parallel plate capacitor, for a parallel plate capacitor, the capacitance is equal to E naught, area over distance. So when I find the capacitance, what's the area? The area is 3 centimeters square. The separation, the distance D, is 1.9 millimeter. And the voltage is 18 volts. So this has to be changed to meters squares and meters. To change centimeter square to meter square, you're going to divide by 100 twice. Because 100 centimeters is 1 meter. So you divide by 100 twice, that's this. There. And 1.90 millimeters in meters is 1.90 times 10 to a negative 3 meters. And the voltage is just that. So this capacitance is E naught. What's E naught? 8.85 times 10 to a negative 12. E naught, parenthesis, area, over distance. $8.85 times 3 divided by 1.9. Well, I can write to 14 10 to the negative 1, 10 to the negative. So it's about 14 times 10 to the negative 13 farads, which is 1.40 times 10 to a negative 12 farads. Why do I do that? Because 10 to the negative 12 will be 1.40 picofarads. And that's what they want. They want you to do in pico. And then the charge in picocoulombs. You see how you didn't use the voltage? Now I'm going to need it. Here. Capacitance is also charge over voltage. So what's the charge? CV. Q equals to CV. What's C? That. What's the voltage? 18. $25.2 picocoulombs. That's the charge, that's the capacitance, and they want you to find the magnitude of the electric field now. How do you find the electric field in a capacitor? There are two ways you can find the electric field in a capacitor. This way on this. To find the electric field, remember this area and this distance. And the voltage was 18 volts. The electric field can be found as the voltage over the distance between the plates, or sigma over E naught, where sigma is the charge density, which I don't think we cover much in this chapter or in this course. But just in case, sigma is a property depending on the type of charge and the amount of charge in a given area. Regardless, E will be 18 divided by the distance, which is 1.90 times 10 to a negative 3. That's 9.47 times 10 to the power of 3, which is 9,470 volts per meter. Quite large, as you would expect, given the separation. All right? And then let's do one with circuits. I want to change the number for this, okay? That's the last problem on the assignment. The only thing about Cengage is that some of the numbers are kind of annoying. There are examples that I did in the previous video, but let's see how we can solve a circuit problem using parallel and series capacitors. So you have, let's see you here. I'm building the circuit right now. Okay, let's make this 6 and 3. Nine and 18. And let's make this 27 CV. 9 volts. Yeah, let's do some 9 volts. Find the equivalent capacitance. The equivalent capacitance of a circuit. So we have parallel. When you have capacitors in parallel, you add them. So 6 plus 3, this whole branch is 9 microfarads. And then you have 9, 18. So for part A, 1 over series is 3 are in series. For series, you do the sum of the inverses. There. Because they're in series, right? In series, the charge is the same across. These are easy fractions. 1 over 9 plus 1 over 9 is, well, let's put here 1 over C equivalent. It's 2 over 9. Common denominator is 18. 4, 1. So that's 5 over 18. I have to flip it. So equivalent is 18 over 5, which is about 3.6. 3.6 microfarads. That's the equivalent capacitance. Let's make this. Let's make this 10 volts. All right, I want to have easy numbers as well sometimes. Why do I do that? Because now I want to find the total charge. The total charge of the circuit. Q total is C equivalent times the total voltage, which is this. 3.6 times 10, 36 microcoulomb. If you're not sure, Because we here, .6 times 10 volts. That's 36 microcoulombs. So that's the charge here, and the charge here, and the charge here. Not for these two, those are in parallel. So let's work with 9. The charge of 9 is 36 microcoulombs. This is the capacitance. Let's call it C1. What about the voltage in this? Voltage is, if you remember, C equals to Q divided by voltage. That means that voltage is Q divided by C. Q divided by C, 4 micro cancels, 4 volts. Makes sense because everything is 10, so that's already 4 volts. What about for 18? For 18, that's a charge as well, 36. So Q is 36 microcoulombs. That's the capacitance C2. So the voltage is 36 divided by 18, 2 volts. 2 volts. 4 volts, that's 6 volts. But we're given 10. So where are the other 4? Here. And what's 4 times 9? 36. So it works. The charge here is 36, right? Now, why do I need the voltage here? Because that's the voltage on 3 and 6. Because they're in parallel. In parallel, the voltage is the same. And why do I need that? Because if I have the voltage on each, I can find the charge on each. So I didn't have to find that. I didn't have to split that charge here and here because they're in series. But when you have parallel, you have to split the charge because here is a junction. So the charge splits top and bottom. Right? So you can find the voltage. If you think about it, you can just divide 36 by 9, and that's 4 volts. 4 volts here, 4 volts here. So 6 microfarads is at 4 volts. 3 microfarads is at 4 volts. So the charge at 3 is 4 times 3, 12 microcoulombs. And here is 24 microcoulombs. 24 plus 12, 36 microcoulombs. So that works. Okay. So this is how you do a circuit problem. It's identical with different numbers to the one that you have in Cengage. Okay. I hope this video is enough. I mean, it's about half an hour. All right. You can add to the other video that is already in there, and pretty much you can solve this assignment. The next video will be about current, Ohm's law, circuits still, but then we will be working with resistors. All right. So I will see you guys later on the next video. Have a good day.